Let's introduce the one-dimensional heat equation. You could think of the following situation. A dye or some other chemical is in a water-filled pipe. So here's the picture. I have a long tube filled with water, and at one end of the tube, I place a bunch of dye or chemical, and then I'm going to watch as over time, the chemical spreads itself out, eventually being uniformly concentrated throughout the water. This is the same as how heat will diffuse through a material. So that's why it's also called the heat equation. But I like to visualize it mentally by thinking about dye diffusing through some water-filled pipe. So let's say the pipe is length L. It's one-dimensional, so there's one axis here, x. Maybe this is at x equals 0. So we're going to let u be a function of two variables, t, which will be time, and x, the location on the pipe. This will be the concentration of the dye at time t and location x. So as you change the location and as you change time, the amount of concentration in the dye will also change. So I have a function of two variables. The heat equation, also known as the diffusion equation, is the partial differential equation ut of tx. Now remember, the subscript t means I'm taking the partial derivative of u with respect to t. That's equal to some constant k, which is positive, times the second derivative, uxx, so the second derivative with respect to x, of the function utx. So this is the so-called heat equation, and I'd like to show you why this is actually true. So why is the heat equation this? Well, the idea is you could take a very small cross-section of this pipe. So take a small sliver of pipe. Maybe I'm at location x, and maybe the width, the small sliver of this pipe, is width h. And let's say that the cross-sectional area, so the cross-section has area capital A. So I'm going to take a small sliver, and I'm going to assume that my sliver is so small that the function, the amount of concentration in the dye at time t and location x, is constant throughout the sliver. So as x changes from x to x plus h, the concentration doesn't change in the x variable. Maybe it will with respect to time, however. So then I could write down the amount of mass in the dye. So the amount of mass in the dye is the concentration times the volume. The cross-sectional area is A, and the thickness is H. So AH is the volume. If I multiply the volume by the concentration, I get the amount of dye in the sliver. So this will be the mass of the dye in this slice. Now, if I take the derivative of this with respect to t, so I'm going to put a subscript t here, that will give me the change in the amount of mass in the dye in a slice. Now, you can keep track of the amount of mass in the slice by calculating how much dye goes into the slice and how much leaves. So the change in the mass of the dye is equal to the flow into the section minus the flow of dye out of this slice. Now, the flow into the slice, I'm going to say is the following. Negative K, here K is just going to be some positive constant that depends on the property of the dye. If you're thinking about this as heat, maybe if you're heating up an aluminum tube, it'd be different than if you heated up a steel tube. So the K is just dependent on the properties of the material. So it's some constant, positive, times A times the partial derivative with respect to x of Tx. Now let me explain why I'm writing that down for the flow into the slice. So I have a negative sign because what I'm saying is that the dye flows from a region of high concentration to low concentration. So that's why I have a negative. I have the K, that's the properties of the dye or the material. A, I'm saying that the amount of dye that flows into the slice is proportional to area. So the more area there is, the more will flow into the slice. You don't necessarily need this area. You could absorb this into the constant K, but I'm writing it explicitly for our next step. And Ux, that's the change in concentration as you move along the x-axis. That's what the derivative tells you. It tells you the change in the amount of your function, the concentration, as you vary x. So this is the flow. It's how much dye is flowing in. Similarly, how much dye is flowing out? I'll write down the same expression, except I'll just replace the location x I'm thinking about by x plus h to have the flow out of the right side of the tube. So this would be negative Ka Ux T x plus h. So now I will divide both sides of this equation by AH, and I find that the partial derivative ut Tx is equal to, I'm going to factor out a constant k in front, and I'm going to put the positive term first. So I'm going to get Ux T x plus h minus Ux Tx divided by h. So I took this last expression, I had divided both sides by AH. I find this. Now you might start to see where I'm getting the second derivative with respect to x. This is almost the definition of the derivative. If I take the limit as h goes to 0 as the width of my slice gets smaller and smaller, I indeed get the second partial derivative with respect to x. So I find as h goes to 0, this partial derivative is equal to k times the second partial derivative with respect to x. That is why the heat equation is a good model for this situation. Now, intuitively, what is this saying? This is saying that the change in concentration with respect to time is proportional to the second derivative. The second derivative of a function gives you its concavity. So let me just try to give you an intuitive reason of why this should be the case by drawing a picture. So let's say this is x, and I'm going to plot the concentration in the dye at a certain fixed point in time. So I'm fixing time And I'm going to take a snapshot of the picture of the dye concentration at location X. So maybe the concentration looks like this. So I have a pipe of length L. Maybe I have higher concentration, more dye in the beginning of the pipe, kind of like what I've drawn up here, and less over there. If you start time, if you watch how this dye diffuses throughout the pipe, eventually becoming uniformly distributed, the areas of high concentration, like this point here, will go down. So an area of high concentration will go down to the average concentration. Area of a low concentration will go up. So where the function is concave down, I find the concentration will go down. And the more concavity there is, the more concave down it is, the faster this function, the concentration will go down. If the function is concave up, the concentration of the dye will go up. So that's an intuitive reason of why there's a second derivative involved. Okay, so that's a derivation of the heat equation in one dimension. We're going to solve the heat equation using Fourier series. Follow me along there.